so far we have dealt with systems that are well behaved, like, so we have discussed so far well behaved systems like ideal gases, ideal solutions, etc. Okay. As long as we are in the limits of dilute solutions, okay, or low concentration of solutes, okay. For low concentration of solutes, in solutions they behave ideally and we don't need to worry, we no need to worry. Okay. But there are certain type of molecules there are for which, okay, so for which we need to consider some special things, like, so for example, if we consider electrolyte solutions, so we know electrolyte solutions, they contain ions, right, and they behave non-ideally. In the solutions they behave non-ideally, okay. So we get non-ideal solutions. Even if the concentration of the solute is low, okay. So usually we get non-ideal solution, and we need to consider activity and activity coefficients, right. Okay. Now we will see that the activity is used to describe the correction to the chemical potential. Okay, when a compound is not pure. Okay. So, we need to consider, we know this equation, but in some different way, okay, like, okay. So, here we know where mu I naught is the chemical potential or standard chemical potential, and AI is the activity. Okay. So, when a solution is ideal one, for ideal solution, activity of the solvent, if we say that is AS, is just equal to equal to its mole fraction. Okay, that we know. Okay. But for dilute solute, okay, activity AI we can write as mole fraction, and we can consider the mole fraction of solvent is X s and mole fraction of solute is X I. Now, so we need to, as we know now, that we need to really consider activity coefficients for electrolyte solutions. Okay. So, for electrolyte solutions, so we will now discuss activity coefficients of electrolyte solutions. Okay, so we will start our discussion, or we will begin with, we will begin the discussion of non-ideality in electrolyte solutions. Okay. And for that, we define activity coefficients. Okay. So, let us consider an electrolyte which, when 1 mole of it is dissolved in water, consider nu plus moles of positive ions with charge Z plus and nu minus moles of negative ions with charge Z minus are produced. Okay. For example, okay, if we dissolve Na2SO4, so Na2SO4 produces, or for Na2SO4, suppose if we dissolve Na2SO4 in water, we have nu plus equals to 2, we get 2 number of sodium ion, and the charge of each sodium ion is plus 1, and we get 1 SO4 2 minus ion. So, nu minus is 1 and the charge of the anion is minus 2, right. Okay. So, if n moles of this electrolyte. In mole of this electrolyte is dissolved in water, suppose, then the contribution of the solute to gives free energy of the entire solution is, we can write, G minus G S is n mu is nothing but n times nu plus times mu plus plus nu minus time mu minus, okay, where nu plus and nu minus are the chemical potentials of the positive and negative ions respectively, right? And Gs is the solvent gives free energy, Gs is the gives free energy of the solvent, Okay. So, we can write, or because the effects of positive and negative ions are difficult to separate, so the mean, we need to consider mean ionic chemical potential, and we define this by mu plus minus, okay, is mu plus minus equals to nu plus times mu plus plus nu times mu equals to nu times mu plus minus equals to nu plus times nu minus times mu minus, okay, where nu is nothing but the total number of ions produced, okay, and this is nothing but nu plus plus nu minus. Okay, so it's, as I said, it's very difficult to separate the effect of positive and negative ions. So we consider mean ionic chemical potential. We define this one as mu plus minus, and it can be written like nu times mu plus minus equals to mu plus times nu plus times plus mu minus times nu minus, okay, where nu is nu plus plus nu minus. Okay. So, we can write the chemical potential of the solute that is contribution from both positive and negative ions is nothing but mu. We can write mu naught plus RT ln A, and we can write this as nu times nu plus minus naught plus RT ln A plus minus, okay, where A plus minus is the mean ionic activity. Mean ionic activity of the solute. Okay. And it is related to the activity A, like by A equals to A plus minus to the nu. So, we can or we are able to write the chemical potential separately for the positive and the negative ions. Okay. Have, so can write mu is nothing but nu plus times mu plus naught but plus RT ln A plus nu minus times nu minus naught plus RT ln A minus, right. So, in the above expression, in this expression A plus, where A plus and A minus are the activities of the positive and negative ions respectively. Okay. Now, we see that mean ionic activity, okay, we get like this, right. A plus minus to the nu equals to A plus to the nu times A minus to the nu. Okay. So, to quantify the concentration of electrolyte solutions it is convenient to use the molality rather than mole fraction, to use the molality, rather than mole fraction. Okay. Now, what we will do, we will discuss about Debye-Huckel limiting laws and then how to calculate ionic strength. Okay. So, next we consider Debye-Huckel limiting law. Okay. So, what is this law says? So, the expression for Debye-Huckel limiting law is log gamma plus minus equals to minus z plus times z minus mod of this times a root over I, where a is a constant term and the value of a is 0.509 for water at 298 K for water at 298 K temperature. So, the value of A is 0.509 for water at 298 K temperature, 298 Kelvin temperature. Okay, and gamma plus minus is mean activity coefficient, I is ionic strength of the solution. And Z plus and Z minus are the charge of cation and anion respectively. Okay. So, what Debye-Huckel theory does? It relates. So, Debye-Huckel theory, Debye-Huckel limiting law, it limiting law relates the total ionic strength which is just a measure of how ionic the solution is and the concentration of a particular ion pair of interest to the average or mean average activity coefficient for the ion pair. Okay. Okay. So, and there are some limitations of Debye-Huckel limiting law. Okay. The limitations. Number one limitation is it is applicable for ions. Okay. So, it is applicable for electrolyte solutions. Okay. Second approximation. Okay. Molecules that are not charged have an activity these are all limitations or approximations. Okay. These are all limitations or approximations for Debye-Huckel limiting law. So, molecules that are not charged have an activity coefficient of 1. Okay. Third one is the charges that appear in the equation are only those of the salt we are calculating. The activity coefficient for. Okay, so there are some limitations or approximations of Debye-Huckel limiting law, like it is applicable for ions only, means for electrolyte solutions. And the second approximation is molecules that are not charged have an activity coefficient of 1, and the charges that appear in the equation are only those of the salt we are calculating the activity coefficients for. Okay. And this is applicable for dilute solutions. Okay. No, so there is deviation of Debye-Huckel limiting law when the concentration is high. Now, what is ionic strength? So, and how do we calculate it? Okay. So, calculation of ionic strength. So, ionic strength we define by I. We define by I. Okay. And it is a measure of the amount of ions present. Okay. And the formula for ionic strength is half times sum over I mi z I to the 2. Okay. Now, here we consider, or in some books you will find that the unit of ionic strength is in molar unit. Okay. And in few other books you will find that okay, ionic strength is unitless. Okay. So, here we consider ionic strength is calculated from concentrations relative to the standard state. Standard state, or we consider 1 molal. So, we consider that I is unitless. So, there is no unit of ionic strength we consider here. Now, how do we calculate ionic strength? Okay. Suppose we have an aqueous solution of NaCl, sodium chloride. Okay, and for that we consider that, okay, so this the concentration is 100 millimolal. Okay, this is the concentration of the solution. Now, how do we calculate the ionic strength of this 100 solution? Okay. So, ionic strength I is half times concentration of sodium ion times charge of sodium ion plus 1 to the 2 plus half concentration of chloride ion times charge of chloride ion times to the 2. Okay. So, half, and what is the concentration of sodium ion here? 0.01, 100 millimolar we consider, times 1 plus half times 0.1 times 1. So, this gives you 0.1. So, this is the ionic strength of 100 sodium chloride solution. Now, we will consider one more little bit complicated example. Okay. Now, we consider 100 aqueous MgCl2 solution, aqueous magnesium chloride solution. So, when you dissolve MgCl2 in water, it gives Mg2 plus 2 Cl minus. Okay. So, concentration of Mg2 plus is 0.1 m, right. Charge, okay, so Z Mg2 plus is plus 2. Concentration of chloride ion. So, 1 mole MgCl2 solution, when you dissolve in water, it produces 2 mole of chloride ion. So, the concentration of chloride ion is 0.2 m, right, and charge of chloride ion is -1. So, what is the ionic strength of MgCl2 solution? So, this is half times Mg concentration of Mg2 plus times charge of Mg2 plus to the 2 plus half concentration of chloride ion, okay, times charge of chloride ion to the 2. Okay. So, you get I equals to half times 0.1 times 2 to the 2 plus half times 0.2 times -1 to the 2. So, you get I is 0.2 plus 0.1. So, the ionic strength of 100 mm aqueous MgCl2 solution is 0.3. Okay. Okay. Now, if we plot, so from Debye-Huckel theory we know, from Debye-Huckel limiting law, we know log gamma plus minus log equals to minus mod of z plus times z minus times a root over of ionic strength. Okay. So, if we plot log gamma plus minus versus root over I, what we get? We should get a straight line, okay, like this up to certain concentration. Okay. So, this is, suppose this is for NaCl solution. Okay. For MgCl2 we get like, oops, for MgCl2 you get something like, so this is for MgCl2 and you can get this kind of plot for MgSO4. Okay. So, for a particular ionic strength, okay, so the slope of this curve depends on this factor, mod of z plus times z minus times a is a constant term. So, for MgSO4 z plus times z minus gives you 4 and you have the minus sign. So, you get the decrease of log gamma plus minus as you increase the concentration or as you increase the ionic strength. This is much faster, right, compared to MgCl2 for which the mod of z plus times z minus is 2 and for NaCl it is only 1. Okay. So, that is how you get different slope for different ionic solutions. Thank you.